Let's make that 10 meters. Let's give this a mass of 15 kilograms. Let's make this angle down here. We'll make it 60 degrees. And we will be trying to make this initially at rest. We'll start out frictionless. So, how much will the spring compress? Now, the reason why this is a lot more difficult, you'll end up with a quadratic first off. So your quadratic formula or whatever technique you use to solve that is going to come in. But as the spring compresses, the gravitational potential energy is also changing. The height is changing as it compresses. And that is something we need to deal with. It is frictionless. The only forces involved here are the normal force, which is doing no work at all because it's perpendicular to the movement. And the weight, there is a change in height, and the elastic potential here, or elastic force here. And so energy is conserved, so I'm just going to jump straight to that equation right there. We have 1/2 mv initial squared plus mgh initial plus 1/2 k. I'm just going to simplify this kx squared initial equals 1/2 mv final squared plus mgh final plus 1/2 kx final squared. My dropping of the delta in front of it, just understand that it's a change. There is movement in the spring. It is not uncommon to drop the delta in this particular case. The notation's, in my opinion, just a little bit sloppy, but I'm just tired of writing deltas. Just so long as we don't confuse what that x is. All right, so what is 0?
Initial velocity.
There's just something about this group that you just hate saying speed.
I'm sorry. It's because you put that V in there, but yes. Initial speed. My bad.
There we go. All right. What else? Initial displacement. Okay. There's one more definitely we can make 0. And then another one that we might or might not want to, depending on how your brain is working at the moment.
Can we make the final height 0 again?
We can. It's some. So this is 0 because Elon says so. There is an advantage, not necessarily making height is equal to 0 there. There's an advantage to making it height is equal to 0 there. It just really, this is the part that really depends on just the way your brain is working at the moment. Personally, I would set h is equal to 0 here, and there was an initial and final height, but that is just the way my mind is working at the moment. However, there is one more thing we can make 0.
Oh, final speed.
Yes. So the maximum compression. X is how far this thing compresses. So that would be X F right there. All right, so we've simplified it down to the same thing we simplified it to before. It starts out with all this gravitational potential, and it ends up with all this elastic potential. H is equal to 0 here. So we need to figure out what is the initial height. Well, I've got a triangle. I have a triangle where this angle here is 60 degrees. That's a right angle there. And my hypotenuse is 10 meters plus XF. So what is the initial height? What was this?
Would it be 10 plus XF sine 60?
Yep.
Yep.
What I put in brackets right there is the initial height. It's the hypotenuse times the sine of the angle, the opposite angle. And that's equal to 1/2 kx of f squared. I actually didn't give a value of k. We'll need that eventually. Let's look at 40 meters per second again. Whoa. Try that again. 40 newtons per meter. All right, so now it's a matter of solving for x. I know what m is, it's given. We assume it takes place on Earth, so I know g, and I know k, because that's given. We have one unknown, one equation. Generally makes math people happy. So it comes down to at what point do you want to plug in numbers? Do you want to do numbers now or do letters now?
Numbers.
Numbers, all right. So I
15 times 9.8. Brackets,
sine of 60 degrees is 0.866 something, so 8.66 plus 0.866. And I'm just gonna write x, just because to simplify my writing even more. It's equal to 1/2 times 40 times x squared. So I have this 15 times 19, which is 147. Okay.
Yeah.
And so now I distribute. I got this thing, this constant out front, I'm multiplying times something in parentheses here, times a binomial. So 147 times 8.66. I assume somebody checked my sine of 60 is 0.86.
I did.
Okay.
So for the first one, that would be, 1,273.02.
Correct.
And then I guess this would be 127.302. X is equal to 20x squared. And now I have a quadratic. It's a math problem. Actually, once I get to here, it's a math problem now.
That would be minus 20x squared.
Oh, get it over to the other side?
Yep.
All right, so it's quadratic, so get it equal to 0, so we get negative 20x squared plus 127.302x, thus 1,273.02 equals 0. And then quadratic formula time. Negative 127.302 plus or minus the square root of 127.302 squared minus 4 times negative 20 times 1273.02 divided by 2 times negative 20. We will get two answers. One of which is the one we want, the other which does have physical meaning, but not the answer to our problem.
So assuming I did this correctly, wasn't counting them, you get, 23.24.
Or
40.412.
40.412,
42.
something's off. Anybody get either of these answers? We should have had one positive and one negative answer. So if somebody else got both of these answers, that means that there's a mistake somewhere else.
You got 11.77 and negative 5.406.
Everybody else get these?
11.77, so.
Alright. So the question is, all right, so first off, it's how far it compresses. This is meters. And the question is, what does the negative solution mean?
Is the negative go all the way down? The portion left on the spring
No,
when it's compressed?
no, there's no information about that. We assume that the spring, it's an ideal spring, so it's not gonna interfere
Okay.
with itself, so the
Okay.
amount of spring that's left really should not be part of the problem.
Okay.
Go back up the ramp.
If it comes down, it compresses the spring 11.77 meters, and then if it sticks to the spring and then it starts coming back out, it's gonna reach that equilibrium point again, and then it's just gonna keep stretching. And so that is how far up it would go if it was still connected to the spring once it hit it. How far up the ramp, not, they're changing height, but how far up the ramp. So that's what the negative solution means. Because we did assume that X was a positive number, that showed up right there. That's the point where we sort of set X as a positive number for compression. Now I can make it slightly more difficult. Like, Greg, that was a, no, you don't want to see it, slightly more
No,
difficult?
go ahead. Go ahead.
All right, any questions on this before we make it slightly more difficult? It's not like you'll be solving something other, it's still gonna be a quadratic in the end. All right, here we go. Let's go a bit of friction into it. Use of K, let's make that equal to 0.3. Yeah, well, don't call it in this slide. All right, so we now add friction. I know that the friction force is equal to, kinetic friction is equal to mu K times the normal force. We've gone through this box on ramp problem. This would ultimately be mu K times mg cosine of the angle theta. So I can find the friction force because I now know mu, I know m, I know g, I know theta, which is 60 degrees. And since we need to know it at some point, what is this number? So it's about 4.5, about 45, 2, so it should be 20 something.
I got 22.05.
20.05?
22.05.
So that's going to be the magnitude of my friction force. I know it's acting up the ramp. So what changes here is where we start. I'm going to leave this here because we're going to tack onto it, but we started with non-conservative work is equal to the change in energy. That's where we started the Ross-Foley problem and the ski problem. I now have non-conservative work. I have a non-conservative force that's doing non-conservative work. So as the box is sliding down the ramp, is this friction doing positive work or negative work? Is it helping movement or taking away from the movement?
Take it away.
It is negative work. So this is negative times that friction force over there, times how far it will go down, which is 10 plus x of f. And that's equal to E final minus E initial. So when I add E initial to both sides, I get E initial minus Fk times 10 plus x is equal to E final. In other words, I have a new term to tack onto the initial energy side. Or I guess I could add it to the final energy side. But this minus Fk 10 plus x minus Fk 10 plus x. And I'm going to erase, no, I'll change it down here. Minus Fk 10 plus x. So minus 10 times Fk, which is this minus 220.5, minus 22.05 times x equals 20x squared. So this is new. This is the contribution of the non-conservative work. It is reducing the amount that the spring will compress because it's losing energy. And so I would expect that my final answer will be some number less than 11.77. It better be, or something's gone horribly wrong. Or, Nobel Prize. So, doing the math here. So I got 127, so we subtract that, we still get the negative 20x squared. And then I've got these two that I'm gonna combine. So, plus
052.52.
Thank you.
You're welcome.
And then combine these two, my x terms, so that's plus, that'd just be 105.252.
Yep.
So x now equals negative 105.252. Try that again. Oh. Who raised me? This is not a wrong statement, it's just in a bizarre order. Let me put it in more traditional order. X squared plus 105.252x plus 105.252 equals 0. Now that's a more familiar form. Negative 105.252 plus or minus the square root of 105.252 squared minus 4 times 105.252 times negative 20 over negative 4. So again, expecting a positive and a negative number. Although it's possible that there could be two positive numbers here. No. I expect a positive and a negative number. Gotta be careful about the meaning of the negative number in this case though.
Ten point 348.
10.348 meters. And a negative solution.
Negative 5.086 meters.
All right. Anyone else got the same numbers? All right. Got it was one other person who got it back.
Thank you.
All right. So it's going to compress now, not as much as it did before because we've lost energy. The negative solution is has lost meaning because it's losing energy the entire time. It loses energy as it goes down, it loses energy when it gets here, and as it's coming back, it's still losing energy. And that second solution assumes that it basically has gone to about here. It's only lost that amount of energy, as opposed to the entire trip. Similar in some respects to the questions that I asked on the first test about displacement versus distance. One of them ignores all the stuff in between, and the other one has to take that into account. Non-conservative work, you have to take it into account. So, final answer. That's about as difficult as like maybe energy problems right there. We'll eventually get into rotational energy, but that's just, you tack on one more term. It's not like you have to worry about it. It's still dealing with conservative stuff. Questions to hear? Oh, black holes. Here we go. All right, let's bring in black holes and do something known as short shield radius. Let's derive the short shield radius, assuming classical physics. And we'll talk about our sun. Planet X, some radius r. I am going to launch something off of this planet. Whatever speed this object has, whatever the maximum speed this object has is the launch speed. I'm not worried about how I get it to that launch speed. All I'm worried about is that I can get it there. So I'm going to get it to some speed, it's going to get shot off. Now, if I take this marker and I throw it into the air, what's going to happen? Assume it doesn't hit the ceiling.
Just gonna come back down.
Yeah. If I throw it harder,
Still gonna come back down.
all right, what about the motion of it?
Up and down.
Yeah, okay. Read my mind.
Leave my mind.
It's going to go farther up before it comes
yes,
down.
yeah.
That's what I was shooting for. So if I launch this thing at say 10 meters per second, it's going to go out and come back. If at 20 meters per second, go out farther, come back. So what I want to know is at what speed do I launch this so that it never comes back? That's the problem that we're going to start with. And it's a conservation of energy problem. The reason why we can't make it a Newton's law problem, well, we could, but it requires calculus. The reason why we don't do it is the fact that the acceleration, once I launched it, the acceleration is not constant anymore. I can't use mgh or mg. We are now dealing with energy, gravitational energy, the generalized formula. Once I have launched it, the only force acting on it is the gravitational force. So therefore, energy is conserved. And I have k initial plus u initial equals k final plus u final. This is why I don't want to worry about how I get it launched, because that will introduce presumably a non-conservative force, and I don't want to have to deal with this. All right. Potentially the last chance for in class to do this, so let's make it good. What's the formula for kinetic energy?
1/2 mv squared.
Okay, a little bit of style there. All right. Now, the potential energy associated with the generalized gravitation. You should nitpick what I just said. What is the potential energy formula associated with the generalized gravitational force? We're at the beginning of class today, as well as last 2 Thursdays ago.
Is this the negative G, M1, M2 over R?
That's the one. That's our initial Now the way I have it listed up here, I have 3 different masses, so let's sort of clarify. This is, m sub x would be mass of the planet, and m sub s will be for the satellite that we're shooting off. I guess especially it's not a satellite since we're not getting into orbit, but. So this is mass of the stuff we're sending, there we go, S for stuff. And this will, the 2 masses here are X and S. And R sub I right here is the initial distance from center to center distance. And that's gonna be equal to 1/2 mass of stuff times the final speed squared minus big G mass of X, mass of stuff, divided by R final. Now, just as a common occurrence, remember that this is negative G M1, M2 over R plus some constant. Traditionally, if it's not stated, it's usually thought of as that the potential energy is equal to 0 and R is equal to infinity. That's the traditional way of doing it. And so, if you don't like that, we can just tack on a constant, which will then subtract off, and we're back to where we started. All right, so what's 0?
Initial speed.
No, initial speed, because it is being launched. Whatever that initial
Okay.
speed is, the speed at the surface is what we're considering to be not 0.
Okay. What's the 0 with the arrow up there? That's just the,
Oh, that's the object that we're studying.
okay.
We're studying a round object, apparently.
Around now.
Final speed?
Yes, because as soon as we launch it, the thing's gonna start slowing down. Now, it's never going to stop, because if it stops, it's gonna then come back. But it is gonna get slower and slower and slower. So it is gonna be so close to 0 that it's gonna be insignificant. So this is 0 because my final speed is much less than